Building retuning training was conducted by Ron Underhill and Gupong Liu, scientists at the Pacific Northwest National Laboratory. Classroom and on-site training for Maryland State Agency facility managers was conducted at Towson University in Towson, Maryland on June 17th through the 19th, 2014. This segment of training covers zone controls.
This section we want to talk about the terminal box control. So terminal box is the setup of the duct and the damper with automatic control to provide thermal comfort and ventilation to thermal zones. So the thermal comfort has been provided by the thermostat to control the temperature set point for the zone. And the ventilation requirements has been met by the minimum airflow set point for the terminal box. So here we can give more information about this. And terminal boxes are one of major building HVAC components for new buildings with VAV systems. So directly they have the big impact for the comfort and the energy use. If the terminal box minimum airflow set point is too high, that can cause some problems. So you have to have a lot of reheat for the terminal box to compensate the problem. For example, like say this conference room, if it's designed for 80 people, so the minimum airflow set point for the terminal box, when they design this, they have to maintain 80 occupancies ventilation requirements. So no matter they have occupancy in this space or not. So that means when this room has not been used, they still supply the airflow, minimum airflow to maintain the ventilation, which can cause a lot of problem. For example, conference room, you run into freezing cold because they continue to supply the high minimum airflow. But if some room you go into that room feel very comfortable, it's probably because they have reheat coil, so they compensate the overcooling issues. So that's why you have a lot of fan energy waste, cooling energy waste, and reheat. So we can talk about more how to find the optimize the minimum airflow set point in the following slides. So if like say improper minimum airflow setting may result in significant simultaneous heat and cooling, actual farm power consumption, and higher energy consumption in summer. So for most control vendors, they set up the minimum airflow cooling minimum equal to heating minimum equal to heating maximum. So that's the default setup. But a lot of energy service providers, they may provide a better solution for that. Because like say this area, at wintertime you can get extreme cold. So at that condition, you may set up the heating maximum a little bit higher, not the same as the heating minimum, because if you don't have the velocities, if it's not high enough, you may have the air stratification. So the space, the people feel very cold during wintertime. So that's one thing. They can cause some thermal comfort issues. And also, they have some space like the conference room, sometimes they set up the 50% of cooling, the cooling minimum equal to 50% of cooling maximum, which is a high number. That can cause a lot of problems when this space is not fully occupied. Let's say if we have like 10 people stay in the office, stay in a big conference room, they still provide, let's say, 2,000 CFM. That can be overcooled, the space. So because terminal box control, they have two P lobe control to maintain the space temperature, to maintain the thermal comfort and the ventilation. The first loop is they modulate airflow set point to maintain the space temperature at the set point. That's the first control loop. So they will reset the airflow rate based on if the zone is too cold, they will reduce that airflow. If the zone is too hot, they will increase that airflow set point. So the second control loop is the damper modulation. So they have a flow station before the terminal box. So that flow station measures the actual flow to the space. So if the zone airflow is less than the set point, so they will open the damper a little bit more. If the measured airflow is much more than the set point, so they will close down the damper. So they have this kind of two pit loop set up to ensure the comfort and also the ventilation requirements. So the airflow set point is reset between this minimum airflow set point and the maximum airflow. So they always change within that range. So the purpose of so we want to collect some information for the terminal box. So we want to see if the terminal box they have a light time setback or not. And we also want to know if there's a significant reheat or not by monitoring the reheat valve position. And also we can know we have the zone temperature and also the zone temperature set point. So we compare these two parameters so we can see if the zone is overcooling or is overheating. And we also want to know if there's a significant reheat or not during the summertime or the cooling season for the parameter zone. We know that during summertime there's no heating requirements for the parameter zone. So if we have the trainer data for the reheated valves, so if you see that heating valve are open during summertime, so that tells you something is wrong. Probably it's because the set point is too high. And we also want to know if there's supply temperature is too cool or is too warm. Also, we have the interest about the zone temperature control. See if the zone temperatures oscillate or not. Some zone temperatures, they may have a very narrow deadband. For example, cooling at 71 degree and heating at 70 degree. So if you only have 1 degree deadband, that can cause you a lot of problems. You can see that that zone being reheat and from the full cooling to full heating, back and forth. So that's another type of simultaneous heat and cooling. So we try our recommendation is to widen that band as wide as possible. But different building has different requirements. Some may have some building occupancies that okay, they want to only feel comfortable between 70 or 72. But we try our best to persuade to widen that range to at least 4 degree. So what's your normal setup for the band? 4 degree? Okay. Yeah, our simulation shows that by widen that range, the savings significant for just by changing that cooling and heating set point. We want to look at the unoccupied mode, see if there's a setback or not during the unoccupied hours. So we review the plots of the zone occupancy command and the heating valve position and the damper position over the time. So if there's a valve modulation or damper modulation during unoccupied hour, that's a good indicator. So here is one of the charts shows the zone before retuning and after retuning. So before the left side chart, you can see that the zone temperature is maintained well, about 72 degrees, 74 degrees, and during unoccupied hour, nighttime, you can see that still reheated valves open during nighttime. So the right-hand side, the chart shows that we can just disable that reheat during unoccupied hour. The green line is the reheat valve command. So you can see that the left side, they don't have the occupancy mode. So what we want to do is enable unoccupied mode control. So Ron has discussed in the scheduling, and we want to turn off the system. So we want to develop a schedule for each zones, and make sure the unoccupied mode is enabled. A good recommendation Ron just mentioned is that for the parameter zone, we can have a good setback. Like say unoccupied hour, we can set up like a 78 degree, 68 degree, and during for the interior zone, we can completely shut off. I mean, all the box we can give a wider set point. So minimum airflow setting is too high. They can leading to excessive reheat. So we want to determine whether the heating valve is open during unoccupied hour, and review the plots or the heating valve and the time. Sometimes the zones can be changed the functionality. For example, office space, they can possibly be changed to a storage space. And the space has been rearranged, especially for older buildings. So that's why the very original minimum airflow set point might not be working for the new configuration. So that's why if you have this kind of system configuration change, probably you want to go back to your mechanic schedule, look at your terminal box, and see if you have opportunity to adjust the minimum airflow set point. Let's say it's a storage room. You know that nobody there. Why still you supply, let's say, 400 CFM to that room, no matter what? You can reduce that minimum airflow to 0, because you know that if the room temperature has been certified, you don't have to supply any air to that space. So that's one thing we can think about to do the adjustment based on the functionality of that space type, the zone type. So this is one more example. You can see the left-hand side, you can see the heating valve position for this terminal box. And the zone temperature is blue line. The red line is the reheat valves. They have the unoccupied reset schedule. But you also can see there's a significant reheat for this box. This is serving an interior zone. Do you think we need that much heating for an interior zone box? Some maybe, but probably a lot of time probably you don't need. Because we know that interior zone, if the parameter zone temperature has been maintained, you don't need heating for that space, because you already have the lot of cooling load from the lighting, computer, internal heat gain, human body. So if we add all this load together, there's a lot of cooling load already. So the minimum airflow set point actually can just maintain that to certify that cooling load. So in most cases, you shouldn't have a big heating load in the interior zone. So that tells you that you may have to re-examine your terminal box configuration, see if the minimum airflow set point is too high or not. So after retuning, you can see that the reheat has been eliminated for that zone. So that means you can achieve this kind of fan power savings by reduced airflow and reheat savings, also the cooling savings. So we want to reduce the interior zone terminal box minimum airflow set point. Some places they may just disable the heating for the interior zone in the summertime. and to eliminate the heating leakage.
So let me interrupt just for a second. So what Gupong's saying here is that if you reduce your minimum CFM settings for your boxes, typical design parameters are generally excessive. And so by reducing it, you may be able to maintain your space temperatures with reduced airflow settings. This can be pretty significant, especially if you can shut off your reheat system. If you can't shut off your reheat system because your minimum airflow settings are so high that when I'm in a non-cooling mode, I've overcooled my space, now I'm going to my airflow setting for heating, and it's so high because I've got it set high. This is the whole idea, is if I can reduce it, I can still maintain my settings, my airflow, but possibly do it without having to add reheat. So
yeah, one thing we can think about, for example, like this kind of conference room, if we add up our occupancy sensor, motion sensor, whatever, so not only just control the lighting, if they can use relay, send a signal to the terminal box, let people know this is unoccupied. Then at that condition, you can write a code to program the minimum airflow set point to 0, because we know that there's nobody in this conference room. At that condition, they won't dump a lot of cold air to this space, so it won't be overcooling this space. So that's one thing you can think about, probably some programming work and some wiring work to control this kind of terminal box. So this example of a starving terminal box for a conference room. So you see the space temperature is set to 75 degrees, but the actual zone temperature is about 70 degrees, because just like I said, there's two control loops. One is control the zone temperature, but another one is they still have to maintain the minimum airflow set point for that space. So that's why that zone has been cooled down to like 70 degrees. So that's opportunity to change adjust the set point. Simultaneous heating and cooling for the parameter zone terminal box. So if you find there's a significant reheat for parameter zone terminal box during summertime, that's another sign tells you that you may have a minimum airflow set point too high. So we can review the plots of outdoor air temperature and the heating valve position versus time, and look at the heating valve position for the temperature is higher than 65 degrees. So this example, you can see the outdoor temperature is the purple line between 60 degrees to 92 degrees. It's obviously in the hot weather condition, and the zone temperature is about 70 to 74 degrees in the blue line, and the reheat valves, it should 100 degrees in May. So this one, you can see that it's hot outside, but it's still a lot of reheat energy waste.
So you're saying in the second graph that your CFM into that zone probably is lower than in the first graph?
Yeah.
So that graph might be better if it had the CFM also on it? So they can compare the two? Just so, but that's what the situation is here, because otherwise there's no difference in the graph, and it's showing that you're going to keep your zone temperature without having any reheat. So that's missing from this diagram.
You mean the CFM?
Yes.
I didn't show the CFM.
Right.
Yes, that's a good comment, because, if we plot CFM here, the left-hand side CFM is much higher than the right-hand side. That's very good comments. If we show that, that can give the whole picture to the audience. And that's what we did, is to reduce that minimum airflow set points because it's oversupplied for the parameter zones. So by doing that, the airflow reduced, and also the reheat has been eliminated during the summertime. Yeah, good comments. So this part we talk about the zone cooling and heating demand. So it's talking about the we want to identify if the supply temperature is too cool or too warm. And also, we can identify if there are certain zones out of control. And so this chart, actually, we should look at this chart combined with the duct static pressure reset, that section. So all those lines are the actual damper command for the different zones. So you can see these charts, most dampers are within the range 50% to maybe 75%. So that's a good distribution of the damper position about all different zones. And this plot shows the VV damper position with the range between like 10% to 100%. So this one is marginally okay because most of the zones has been certified, but still you can see one or two zones cannot be certified all the time. So in a lot of cases, people may just use the constant static pressure just to maintain that couple of zones, which is outliers. This is called this kind of one zone or two zone. They drag the tails. So this chart shows almost all the zones are 90% or to 100% open. So that means the static pressure could be too low. So we have to increase static pressure a little bit so we can make the dampers close a little bit more because those zones might be starving for the airflow. And this chart shows that too many zones dampers are fully closed position.